Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over molecular orbital energy level diagrams for homonuclear diatomic molecules in the alkali and alkaline earth metals. I'm going to go over a couple of example problems, so let's get into this. Okay, so for the first problem, it says use a qualitative molecular orbital energy level diagram to predict the valence electron configuration, bond order, and likely existence of Na2 minus ion. Okay, so the first thing we need is a molecular orbital energy level diagram, and we happen to have one here. It's generic, meaning that here we have N instead of 1s or 2s or anything like that. So since this is sodium, it's in the group 1 elements, right? So it's an alkali metal. It's in period 3, right? So this would be N3. Let me double check to make sure I'm right about that. Yep, that is correct. So this would be N3. So this would be a 3s orbital for this sodium and a 3s orbital for this sodium. But since we're dealing with an alkali metal, any alkali metal, we're gonna have it in the first group, and therefore we're gonna keep this generic because this will apply to uh, all of the alkali metals. Okay, so first thing we need to do is fill in with our valence electrons, fill in the atomic orbitals. So we have sodium here. Sodium is in group 1, so it has one valence electron. So we'll put one valence electron there. Here we have sodium minus, that's a sodium ion with a negative charge. So normally it has one valence electron. So if it was one valence electron, that would balance the charge. It would have zero charge. But since it has a negative charge, that indicates it has two valence electrons. So that's going to be spin up, spin down. Excuse me. Okay, so now that we have the valence electrons for the atoms set up, now we can take those valence electrons and fill in, excuse me, fill in the molecular orbital energy levels. So we're going to start with the lowest energy level, sigma ns. This can hold two electrons, so we'll put two electrons in there, spin up, spin down. So we have three total. We used two, so we have one left. The one has to go up into the anti-bonding orbital, like so. And so this is what the molecular orbital energy level diagram would look like for Na2 minus. So now we can figure out what the electron configuration is going to be for the valence electrons. Now, the valence electron configuration, as it says, is just the electron configuration for the valence electrons, excluding everything else. This is not the same thing as an abbreviated electron configuration. An abbreviated electron configuration is an electron configuration where you have the noble gas in brackets followed by the valence electron configuration. The valence electron configuration is everything minus the noble gas. So it would be the same as if you would write the noble gas electron configuration and then erase the noble gas. What you have left is the valence electron configuration. So here, since we're dealing with 3s and 3s, the 2p and the 2s and the 1s are all non-valence electrons. They're in the core, so we're ignoring those. And so we're just going to write what the valence electron configuration is going to be. And then, so that would be filling in from the bottom. So we'll write out Na2 minus. The valence electron configuration is going to be sigma ns, or we could actually do 3s if you want to be specific about it. So it'd be for this, it'd be 3s with two electrons, and then we have the sigma 3s star with 1 electron. And so that would be the valence electron configuration for the Na2 minus ion. What about the bond order? So bond order is going to be equal to the number of bonding electrons. We have 2 in the bonding orbital minus the anti-bonding electrons. So we have 1 in the anti-bonding orbital and then divided by 2. 2 minus 1 is 1. So that's going to give us 1/2. So we have a bonding order of 1/2. And so to the last question, what is the likelihood of the existence of this ion? Well, since it's a bond order of 1/2, that means it has like a half a bond. So the bond is there. So this will exist. However, that 1/2 bond is pretty weak. So very easily breakable. So I would predict that even though this exists, it's probably going to be very highly reactive because that bond is so easy to break. So that's it for this particular problem. Let's go on to the next problem. Okay, so now for the second problem. In the second problem, it's pretty much exactly the same. Now, instead of Na2 minus, we have Ca2 plus. Now we're dealing with an alkaline earth metal. So alkaline earth metals are in group 2. So they tend to have 2 valence electrons. They're going to have 2 valence electrons in their s orbital. Calcium is in what group is it in, or what period? It's in period 4. So the valence electron, the valence shell or valence orbital would be the 4s. So these would be 4s's, but we're going to keep this generic. This will apply to all the alkaline earth metals that form this sort of molecule. So it doesn't matter if it's a 1 or 2 or 3 or whatever. Okay, so here we've got calcium and we got calcium plus ion. They're going to form a molecule Ca2 plus. So calcium has 2 valence electrons in its 4s. So we'll put 2 valence electrons there. Calcium normally has 2 valence electrons, but since we have a positive there, that means it lost 1 electron. So it only has 1 valence electron. So there's 1 there. And now we're going to fill in the molecular orbitals from bottom to top. So this sigma ns, or sigma 4s in this case, orbital is going to have 2 electrons. So 2 go in there. We have 1 left. So that 1 is again going to go into the next higher molecular orbital, and this is going to be the anti-bonding orbital. And so now this is how the electrons are filled for our molecular orbital energy level diagram. And so now that we have this filled, we can go ahead and answer the questions. What is the valence electron configuration? Again, for calcium 2 plus, we're going to start with the bottom. So the bottom is going to be sigma 4s with 2 electrons. And then we have 1 in the anti-bonding orbital. So that's going to be sigma 4s star with 1 electron. So that's the valence electron configuration for this ion. Next, the bond order. So again, it's going to be the bonding electrons minus the anti-bonding electrons divided by 2. So we have 2 bonding electrons minus 1 of the anti-bonding electrons. We have 1 up there divided by 2. And again, that's going to give us a bond order of 1/2. And once again, what does this tell us about the likely existence of this ion? it tells us that it is likely it will exist with half a bond order. So there's like a partial bond to this molecule. But again, because it is a partial bond, it's a half a bond, it's going to be a very weak bond. And so I would predict that that's going to be um, highly reactive. And so again, these are a couple of examples to show you how you could fill out the orbital diagram for various homonuclear diatomic molecules for your alkali and your alkaline earth metals. I hope this was helpful. Excuse me. If this video was helpful, if you enjoyed the video, if you learned anything from this video, then please like the video, share the video, hit that like button somewhere around here. Also, do me a favor, subscribe to the channel if you haven't done that yet. Click that notification bell. When you do, click all and make sure that you click all so that way you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions if you got them. If you have a question or a problem you need help with, or if you have a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.